Okay, so it starts now. There's a time lag in what I'm doing here and what's getting there. This is less than 1 meter, and it amazes me that this computer from HP hasn't been able to take into know it to fix such technical snags. I mean, there is no thousands of miles involved here, so why would things be relayed with such a perceptible, grossly perceptible time lapse? And so it is bothersome, isn't it? And we'll give it a shot how it all comes out when we finish this video and check it for ourselves. So I was reading through one of my articles that I wrote in the year 2010, December, so that's like about 6 years ago. And this is a physics-based article, although it is written quite simple tone, quite simple and comprehensible to the layman kind of ideas. And I got pretty enthusiastic when I was thinking of recording myself and talking about this article. But by the time I set the environment, the lighting, the camera and the cat and stuff, it seems the enthusiasm is gone. I don't know why I have a stage fright like that, even if no one is around. I'm just talking to the camera, and why would I lose it? So there's some sort of fear when you are conscious that you're being watched. So we can't do much about it. We'll see how it goes. But I don't have much visual aid here, much facility of putting a very visually attractive exposition, and I have plenty of space available here, but don't have a facility, so I can't really stand and talk and wave the hands in various ways that I'm capable of. And so let's just begin reading this article, and I would not be looking at the camera because the browser space would be taking all the desktop area, and so let's see how it goes. Maybe I minimize it to some extent, so I still have a view, a check on how things are looking. They're not looking quite weird as I'm capable of. So here's the article. Stephen Hawking, Einstein, and my ideas, written the 4th of December 2010. Thinking about time and relativity, it just passes my own thinking that Hawking has merely made accessible most of the elegant and yet incomprehensible genius of Einstein. But thinking more about this, it also occurs to me that Einstein was not thinking in terms in which Stephen Hawking or anybody explaining his theory was. Nevertheless, Hawking's work is in itself the work of a genius, because explaining the not so simple, after all, work of Einstein can only be achieved by a genius of Hawking's caliber. Hawking's clarity, width, and unimaginable access to all the physical ideas of our universe and comprehensibility is a trademark, a sign of uniqueness. On the other hand, truth be told, Einstein's was not the last words on physical world, neither were they the highest kind, as is often understood by general massive popularity. To shed light on how Einstein actually thought and his own account, I come across it more than a decade ago, and I still remember, thankfully to my own nature, in a book written by Einstein himself, which I had never owned, so I really do not have a copy by myself. Truth be told, Feynman was a greater genius than Einstein himself, and he actually thought in ways which had no space-time quantum parallel Therefore, his genius is still debatable, and his works are only but a tiny account of what he was. So see, this is just my opinion. Well, of course, you can say opinion based on certain first-hand knowledge of the physics, because Feynman was a master genius of quantum mechanics. This is not written in the article, I'm just talking verbatim. But Einstein was a master genius, a great grand genius of the ideas of classical mechanics. Classical mechanics, special and general theory of relativity are just classical mechanics. They're not modern physics. They're not the modern mechanics that quantum mechanics is. And there's a vast deal of difference. There's a vast deal of difference which brings into account the actual level of difficulty, and you will certainly agree that the classical mechanics regime is very, very less difficult than what quantum mechanics or the modern physics is. Mathematically, as well as intuitively, aesthetically, philosophically, and in pretty much any way that you can envisage. Okay, here I stop the verbatim. Now let's get back to the article and read from there. Okay, so how was Einstein actually thinking? The humor is Einstein was thinking in ways loved by every woman on earth. I wouldn't know why I would make a joke like that, even those that did not know him. So a true account is only achievable by his own women, of whom he had a few. And these accounts are pretty well documented as well. But given that there are signatures of how a man, and a woman if you may, thinks in his own works and in his own words, here's my account of it from the way Einstein thought about it and the way Hawking thought about it, to my own ways. My own ways I can always talk about as long as I am alive. It does not need special arts works, just needs a little thought. Hawking, in his recent grand design, of which I have a copy by my side, but I do not bother opening, I have read through its chapter 5, Theory of Everything, and I proudly own this marvel, but here's what I read. Some of the accounts in this book is also sometimes found in many other texts. So we scientists are a bunch of folks who often do not have the facilities to come up with strikingly new explanations and new paradigms. In case of Hawking, though, he comes up like 2 or 3 every page. So before going into the idea of special relativity, I jump with a lesson into its explanation of what a so-called M theory is. M may stand for mad or marvelous per your test. In this, it describes how our universe is one among a billion of such as proposed, albeit timely and temporarily by M theory. But given that we hardly see one, he proceeds to describe the multi-dimension world of ours, where the unproven yet state-of-the-science idea of 11 dimensions is a proposition. He takes a very ordinary yet worldly example of a straw in a glass, a blue Hawaiian. Or was it Blue Hawaiian? Those who did not know, Blue Hawaiian used to be one of my favorite, that's why I mentioned it. And he put that picture in 3 instances in his book. Close, farther, and farthest are from the waitress's account, as understood by Hawking as farther, closer, and closest. In the closest scenario, that is one where Hawking is sitting and drinking the straw as a 2-dimensional reality. If an ant is gradually crawling up the straw, it would have to make a longitudinal movement as well as a circular movement. It goes up the straw and it goes in circle, the face that's open. So very merrily, without any mindfulness of Hawking's watch on his wrist, the ant goes around and round and maybe reaches the surface of ecstasy. It just gets to taste some of the drink there, the ant. And Hawking is watching, so the ant is mindful of what his watch is reading. In the farther scenario, the next level of distance, Hawking sees the longitudinal reality of the straw quite well. The circular reality is obscured by a significant factor, but still seeable from its distance. So Hawking thinks maybe the ant is still crawling up the straw, but it needs a magnifying device, like a powerful digital camera or a telescope, which has a chance to find this ant, given it's on a horizon accessible by the device. But in the last scenario, the situation is quite different. First of all, it's a string theoretic view of the reality. Here enter the social activist as well. Let's say the most honorable one, you name him, and he or she proclaims to be reading a great deal of scientific manuals in college, after which he got embroiled in vicious social dimensions and forgot what it is all about. So he forgot his science because he's out of the academics, he's into society. Then he comes forth in his old age and sees Hawking explaining a new scientific understanding and exhilarates with the prospect of taking part. Hawking then explains, although by common sense I know that it's the same straw that's put in different place, and in this case by the wet race, the intelligent design is quite clear and acceptable. But the distance distorts the view of reality. The circular reality of the straw is suppressed, and the ant may be present which we do not necessarily know. Now the two-dimensional straw is coming out as a one-dimensional objective reality. This objective reality is not to be confused with an objective desire, which is like a pay hike for a sorry piece of work, or your most likable sexual imagery. So this is just one example of how we may have a view of reality that does not conform with the reality itself. Nevertheless, we are pretty sensible in discussing this. That's what these string theorists or ant theorists are doing. They're pretty sensible guys, although in circumstances as visible to the roughly common populace in any community, they are kind of activists of modern-day Holy Grail. The unification syndrome that persisted through 8.5 decades. But the comprehension that's come forth to us non-stringlings, that we live in a world, the reality of which is actually 11-dimensional, and with one dimension is time, the 3 dimensions are spatially encroachable by us all, and 7 dimensions are little turns and curves at a scale so suppressed. The only sensible example we can give is a straw of Hawking or a membrane of a drum on which an ant can experience musical spanking. For a little time, the ant jumps onto air, without knowing its feet are detached from the fibrous membrane that crushed its tiny feet. It may then be so small that the various dimensions of the world reality at that scale show up in dramatic power, and the ant struggles and learns a new game of random walk. Yeah? We might have learned a little game of random walk ourselves when we were all babies, except we are a bunch of intelligent design ourselves, because Papa brings in home a well-fun cart or bicycle on which Munna and Belinda can enjoy Papa's elation in seeing his babies move instead crawl. But imagine a world of different civilization. We just don't know what it would be like. Maybe the baby jumps every other way, crawls up the walls and roof, well down under the roof like a spider creature, and shouts, "For God is Papa," and peace to the sky, because gravity is repulsive. Whoever knows what the reality of a different universe is. So here is the idea of special relativity that Hawking tried to explain through various constructs that are pretty much found in many science popular, like the all-pervasive ether of the Maxwellian and its recanted experimentation by Michelson-Morley setup. He explains the relativity of time by a setup in which light ray travels back and forth between 2 bounds, and in one scenario this is at rest because the observer is not moving with respect to this setup. In the other scenario, the observer and the clock, this time a light ray traveling back and forth between the 2 bounds, are in relative motion. That is, they're in motion with respect to each other. Now, consider Einstein's account. He straight away came with the physical insight. Call it an assumption as well, but its elegance can never be overruled. But space and time are equivalents. That is, if we define time to be a process, then it involves space. It only makes sense how much length is traversed, and that in itself is equal to how much time passes by. If velocity keeps on changing, then time interval and space distance adjust themselves. He then dropped another assumption to the world, which is the speed of light of electromagnetic communication, cosmic radiations, etc., constant speed at which the natural relays of information and disturbances take place. Together, the space and time equivalence, that is their equal validity, and equal reality as far as they occur as a natural process, and the speed of light as a universal constant is the speed at which natural information relays itself, or speed of field disturbances, is summed up as a new theory of physical understanding of our universe, and it's called special theory of relativity. As a more general understanding that emanates from Einstein's genius is available to scientists called a general theory of relativity. To summarize, time was before this understanding held as an absolute quantity. That is, time passes on its own. Time passes on its own. Time is an independent whole in the workings of the natural design. Actually, humor apart, I mean time passes on its own. This is the basis of the ideas time and tide waits for none. But hang on, if you have come up to this point in this article, you will see how no one waits for time either. Why this is the day-to-day implication of special theory of relativity, and why I'm regarded as a truly mad scientist. Well, I may not be regarded like that. It all depends on how someone would like to see you, and it's all subjective. I'm just going to move on here on a bit. So, what's the absoluteness of time? It means time is there on its own, by its own, for its own. Time, like it or not, flows like that, hence must be regarded independent of what we think of it, how we measure it, etc. For example, if I can measure time from two different scenarios. Once, when the car was moving, and I'm sitting in the car, and the other instance in which I get down at a stop and check my wristwatch. In each instance, I thought my watch ticks at the same rate. At least that was the notion until the year 1900, when Einstein's work in 1905. The so-called annus mirabilis, or era of miracle, this understanding or notion as you may, received a severe blow via the new understanding that time in itself does not make a physical sense. It only makes a sense in connection with all of the physical variables, therefore space as well. Something which most physicists forget or never knew is that time is equivalent not only to space, but equivalent to momentum, for example. Now, where did that idea come from? You don't see that in your textbook, and you don't know it's correct or not, but you might give it a shot. Why not? You cannot specify the momentum or the velocity of an object to arbitrary accuracy without making at the same instant, the time instant, a large error on how much time this requires to be noted on your data entry book. For example, in physical reality, if you have a force which is only as feeble as the kick of an ant, you don't talk about a momentum of that kick that brings Lalu Prasad Yadav on his knees, except if the ant were doing something else to him. The ant isn't capable of kicking Lalu Prasad Yadav too hard, but it can do other things, of course. It would take infinite time for the ant to kick Yadav so hard that he realizes his crime. Okay, that's an Indian phrase, so pardon me for putting into an English-based article. That's a tribute to the great statement we have produced, where I have lived a couple years, and the realizing granny is an idiom all over India. So that's because all physical equations have to be consistent. So some of the equations have been formulated just to check the consistency or lack of it. There are plenty that haven't ever been formulated. They are always in need of brilliant physicists like Feynman for a formulation of physical equations and the consistency check. That is why we learn about the famed uncertainty equations, which relates position and distance with momentum, time with energy, and angular distance to angular momentum. But there are actually numerous others, and in reality, everything is mixed up with everything else, except the ones that we know are exactly like that, and no change is allowed there. The basic idea of quantum mechanics is to allow all possibility and not allow any inconsistency. And this is something that was actually noted by Feynman himself. So the ideas should be used because they are easy to remember and understood, and then painstakingly everything is worked out before a new invention or discovery can be made. Those who start with equations will meet an obscure kick in their ass for being too much of nothing. It better be a little of everything working backwards and achieving something sensible. But those who are masters of falsification, see my article on falsification, which includes all scientists, need the equations as well to counter shoddy conclusions. So equations must all be worked out, and those who do so as a matter of profession are called as theoretical physicists or the theoreticians. On the other hand, I am an experimental physicist, and most of my insight goes into the details of how to carry the extensive job. But in preferential terminology, we're all physicists and we know how to alter ranks. So Feynman was a great thinker and theoretician, while he knew how to do certain experiments better than the professional experimentalist. On the other hand, the world hasn't seen much of my theoretical bent of mind, at least how much I know how to solve the problems, like a hardcore theoretician. I'm saying because I'm just a bit passionate to do some of these things on a more serious basis, not just being boisterous here. Einstein was a theoretician by profession, and he formulated and widely used many thought experiments or Gedanken experiments because all experiments can't be carried out. A simple example is how a person would experience free fall if the string of the elevator were cut off. Yeah, that's the example of a Gedanken experiment, a German term for a thought experiment. You don't want a real person to be in that predicament because it means gravitational splash, but in an imaginary experiment like this, you can still go ahead and think through all the consequences of the laws without being inconsistent with anything. One of the situations where Feynman's ideas to take all possibilities and discard the inconsistent ones of the particle physics processes, the theory side is filled up with situations where one draws the so-called Feynman diagrams, and the experimental side is filled up with situations where one considers many processes and discards the ones that do not make a qualification for some way or other. These processes are inherently quantum mechanical in nature. Therefore, by employing such simplistic ideas of inconsistency after taking all possibilities, we arrive at effective solutions, and interestingly impressive ones, much quicker. If we were to use famous equations, we may not even see a signal. Nevertheless, this may be used to invalidate something or as a constraint to reduce the background processes, the ones which hides true signal processes. So this is a very technical thing in particle experiment or in theory, that you use famous equations as a consistency check. You can use it as a condition to remove unwanted things from the intensive amount of data. But Feynman's approach was more philosophical in nature, where you take all the possibilities of the physical thing happening, physical kinematics happening, and you try to find out the inconsistencies and remove them. And that's a much more effective way of doing physics. That's what I'm trying to say. Now, let us go back to the idea of relativity of time. Einstein's idea is therefore time is relative. That is, it makes sense with respect to how it's measured, who measures. A person traveling really fast measures this, or a person moving slow or standing still with respect to time measures it. Now this idea of moving with respect to time, not with respect to clock, but time, isn't heard of because that's my idea, patented, but I will unpatent it soon. So let's go back to Einstein's idea. If the clock is placed in the train, in which you are present, since you and clock aren't actually moving with respect to each other, the rate at which time flows is fastest. So when you were at rest with respect to something else, the time both of you observe about each other will be same and is the fastest compared to what other time is possible if one of you were moving. When you're moving, time will slow down. time is fastest in a rest frame, faster in a slower frame of reference, and slower in a faster frame of reference. So time slows down when objects are faster, but time is being measured from a frame which is at rest with respect to the faster object. It's a bit more technical than it sounds, and I'm not explaining everything bit by bit. So this is just like a simple language, partly, meta layman kind of language, partly technical. So it's just a thing I wrote for partly prepared people. In the first instance, space is as much as you see it, means time clicks at a rate which is more than it would if space is elongated or widened because you are moving with respect to space. So my idea is you are moving with respect to time because space and time are now equal. Somebody can say you are moving with respect to space, and that's Stephen Hawking. So you see the difference in the ideas of different scientists. They're equivalent in what they will give you, but this is just the approach which differs. What Hawking says is, since in a frame in which you are moving with respect to space, which corresponds to the time, you want to measure the delay in relay of information going back and forth between the ends of space points are going to be increased, hence time is slower. So things are moving apart, distance is increasing, more and more distance has to be covered, so more time will be taken, the response of the signals will be slower, so time is slower. Time, or the clock, is ticking at a slower rate if things started moving. It takes more time each time to tick, crick, crick, crick. That is, time is slower with respect to a fast-moving person. That is why if you are on a Shatabdi Express or Shinkansen all your life, you leave it a little longer. Only a little longer to say, haram haram hai. Laziness is despicable. You have been not making any slack in your duties. You are so fast, but like a joke you die the next instant because that's the only time you save by being fast enough. So who says time and tide waits for none? Einstein now says it's also the other way around. No one waits for time or tide. If time is slow because I'm moving fast, I'm actually not waiting for time, so always move faster. Now this was not Einstein's idea, as Einstein thought out how he thought of this is, as I've said this before, space and time are equivalent. Therefore, if you are moving with respect to space faster, it means space is moving faster with respect to you, so time is moving faster with respect to you. Now why he came up with this idea, time and space are equivalent, that nobody can say, not even his legitimate wives, but that's just characteristic of him. And how did I come up with this explanation? Nowhere else you would have seen this explanation. If you move fast with respect to space, since space and time are equivalent, you are actually moving fast with respect to time. Therefore, time and you are on relatively quick motion. If you know it's you that is moving fast, time is slower. And if you know you are slow, time is fast. Special theory of relativity, time dilation. Why would Feynman think of what he would think? Arlene can't say, Grant can't say, neither the nude women on his portrait. Feynman said as much as he could, then he left us, so read his accounts. When Hawking says are Hawking's characteristics. My idea is not only we move with respect to time, but that time happens like a wave. It happens like a particle too, and time can dilate or elongate like space does. If you have a momentum which is precisely known, it means time has to be imprecise, or correct me if you can, but time is anyhow related to energy, and energy precision would mean time window is quite large. Therefore, something moving really fast is almost unseeable. The correct time window it permits is quite small. If you don't see in that small time, you missed it. If it's a baseball or a cricket ball that is moving really fast, then you need to see it with intense light. Then its complete trajectory shows up. Like in a baseball match or cricket match. Else it's just a little here and then a little there. That's what they say, discrete. in quantum mechanics, trajectories and everything is quantized. It becomes discrete, they're not continuous. If it's an elementary particle, then it's a bizarre scene. Intense light will sufficiently alter the motion of the particle itself. Less intense light won't help at all, as its momentum is really small. There is a trade-off, as it is consistent with the uncertainty equations, all of the equations plus the ones that we don't know so far. I tend to think there are actually more equations of uncertainty that we know. Well, the commutation relations extend to more variables that nobody computed all of them. Only if one can invent new homework problems. Physics is intrinsically difficult because there is just so much. Now this is all quantum mechanics. What is the idea of time and relativity? Well, as I said, time is like a particle, which means time in itself is measurable because there is, say, an electron or any other elementary particle. The electron and the photon and all the other little bunnies, they all jump, circle, wobble and dance like they would, permitted by nature's laws, but they all pertain to time. Since time is like a matter particle, if you move really fast with respect to an electron, the electron is moving fast with respect to you. Therefore, the relative motion with respect to each other, time and you, is faster. What's the use of such an idea? That time is like physical matter itself. Is to say there may be an inherent and multitude of new laws just hiding there, which our great masters of science might have hinted to, but we all have so far not been able to find them out. We haven't taken enough pain to clearly see something and work them out, so that there is something really as interesting as a new quantum mechanical phenomenon and its equations. This is the present situation with all of physics. We are boastful of huge machines and huge missions into the cosmos, but we don't have a satisfying answer to some of our most desired questions about nature, the likes of unification included. One of the use of this electron working like a sense of time itself is in another subject I tried to touch without any further serious thinking or work, is the magnetic monopole. See my article about magnetic monopole. Here I have tried to imagine that two electrons, only when they move with respect to each other, even if infinitely apart, just be there, they do start making any sense of time whatsoever. Without that, that is with just a single electron, time would be absolute. So it's not even touching the knowledge of special theory of relativity. But when there are two, whether or not they move with respect to each other, a sense of time develops. An idea from graduate student days, because I had nothing to do, so just sitting there thinking, writing up from 2006 or 7. This is all speculative, but without going through all the calculations much in the Feynman-stick, where we don't see what problems of inconsistency we face with the present understanding. So now these are two electrons or two electric charges. The equations of electricity are symmetric with respect to each other, but the magnetic charges or monopoles are not seen in reality. In reality, there are always dipoles, as known so far. That means the magnetic dipoles somehow disturb the equations of electricity by altering the way time is pictured with separate electric monocharges. It's just speculative again, but this is characteristic of me, and I don't need a wife to remember this and tell you. I just mention as I go. I'm pretty sure that throughout the article it hasn't been as enthusiastic as I was speaking what I wrote, because there were technical and philosophical issues, technical and philosophical barriers in comprehending the ideas here. But if you sit in there, read through it, and put your comments out there what you assimilate or not, it'll be more easier or realistic and desirable on my part to see what this article is really saying, so I can make sense of whether or not it is making enough sense in everything that has been said. Thank you.